So if you had a chance to look at 1 through 12 and there's something you would like to talk about or get some greater clarification on, we can handle a little bit of that now. Reminder again, the 1 through 12 is not due until Sunday midnight. All you have to do is put it in the content library under the homework tab. That's all you need to do for that. But we'll take some questions today. Joe?
Could you go over number 6, please?
6. Sure. No problem. So for 6, it says find the domain of the function algebraically. Express your answer in interval notation. Okay. Well, because the first thing I'm going to do is I'm going to start by figuring out the implied domain. Since this problem has no context to it, it's just like a function that's written down, I know that the implied domain is all real numbers.
That's the negative infinity and positive.
Yeah, exactly. And then to figure out the relevant domain from that, I'm going to look at the specific operations that are going on inside of my function. So in this side of this function, I have subtraction and I have squaring. So I'm going to then ask myself, okay, if I square 2 real numbers, can I ever get something that's undefined? Like a real number multiplied to a real number, that always gives me another real number, right? Okay, so the squaring doesn't restrict the domain any. What about subtraction? If I subtract a real number from a real number, again, always going to get an answer. So that doesn't restrict the domain any. So my relevant domain is the same as my implied domain, and I'm finished. That's it. So the only 2 operations that we've talked about that can restrict the domain are square roots and division. Square roots have to be non-negative, and division has to be by a non-zero, right? The divisor has to be non-zero, or the denominator of our fraction has to be non-zero. So if we looked at 7, 8, 9, or 10, all of those would have some restrictions because they all involve either a square root or division or both.
So if there's no restrictions, does that mean that the relative domain is almost always going to be the negative infinity?
It'll be the same as the implied domain.
Yeah, okay.
Yes. Whatever the implied domain was.
And then, okay, all right.
Jack.
We do 10.
Sure. So 10, we have h of x equals x minus 1 over the square root of x. So again, just like in the previous problem, the implied domain here is all real numbers. Rami?
Yeah. What has to happen for the implied domain to not be all the numbers?
It'd have to be like part of a story problem where the variables would, what the variables are representing would have to be like real things that maybe couldn't possibly be positive or negative or whole, would have to be a whole number or something. Like if x was representing people, you can't have negative people, you can't have decimals of people, right? So that's an example. It'd have to have some kind of story surrounding it.
How would you represent not having decimals? Because you guys have like 0 to infinity for something like people.
So there are other number sets other than the real numbers that we would have talked about in our prior algebra courses, like the natural numbers. So you'd represent the domain not with an interval because the natural numbers are not continuous, because there's gaps in between every whole number. So there's a different technique for doing that. It's beyond the scope of what we're doing here because we're assuming everything is kind of continuous in this course. But there, like the symbol for the natural numbers was like the n with the double bar in it. And I would just use if it were me, I would use that notation or just write it out and just say, would not use symbols because I can't use an interval to do that. You could just write, all the, non-negative whole numbers. And that would be appropriate even. Yeah, back to this one now. So if I look at this problem, I see three operations. I see subtraction, division, and a square root. Agreed? Now, the subtraction we know doesn't have any impact. We just talked about y a moment ago. But the division does. So I know that everything in the denominator, that denominator cannot be 0. And the square root does, because I know that everything under the square root has to be non-negative. Is that okay with everybody? So this one is from the stuff in the denominator, and this one is from the stuff under the square root. So far, so good? So I can solve the square root of x not equal to 0 by just squaring both sides. And x is greater than or equal to 0 doesn't require any solving because the x is already by itself. Now here I can make an observation that saves me a lot of time and effort. So if I have x is not equal to 0, and also that x is greater than or equal to 0, if I combine those together, that's just that x has to be greater than 0, right? Because the not equal to 0, we lose the or equal to from the other inequality, right? Is that okay? So there I'm down to just one inequality, which is nice because it's less intervals to write. So x is greater than 0. My interval starts at 0 and goes to positive infinity. And I'll use parentheses for each because the infinity always gets a parenthesis. And the 0 is not greater than 0, so it shouldn't be included in that set. So it gets the parenthesis there. So that's would be our domain for that one. Is that okay, Jack?
Yeah.
Okay. Joe.
Can we do number 12 actually?
12?
Yeah.
Sure. So I'm going to do 12 algebra. I'm gonna do this algebraically. The directions for 12 don't require you to do this algebraically. So like if you graph this on your calculator and use the picture to figure out the range, that would not be inappropriate since it doesn't ask you to specifically do this problem a certain way via the instructions. So if you're like, yo, all I did was look at the picture and figure out the range, that would be fine. I'm gonna do this algebraically because that's kind of the way that we talked about doing it in class, so it matches. But just to let you know, this is maybe more work than you really need to do if you just are able to look at the picture. And we'll talk about what I did to look at the picture afterwards. Okay?
All right, sounds good.
So if we're going to do this algebraically, I need to first know the domain. So again, there's no context to this, so the implied domain is all real numbers.
There's only context in story prompts, right?
Yes,
Okay.
that's a fair way, or yeah.
Anything else other than story problems?
Only if the variables are representing some quantity, some specific quantity, like where x is representing like people or the measurement of something or money or like those are, if it has some context where the variables mean something other than just like numbers, if they're representing some other quantity, there's context, and then you have to worry about it a little bit. But if it's just, if it's just a variable and the variable has no meaning, there's no context to it, so it's just all real numbers. Does that make sense?
Yeah.
Okay. So if I look at the operations involved, I see subtraction, I see addition, and see square roots. The only one of those that I have to worry about is the square root. So I'll just take all the stuff under the square root and say that that has to be non-negative. I can solve that inequality by adding 3 to both sides. So I'm left with x is greater than or equal to 3. So I can write my interval then for the domain, which goes from 3 to positive infinity. The infinity is always going to get a parenthesis, but because 3 is greater than or equal to 3, I'll put a bracket on the 3. So there's my domain. Now what I need is to look at my, to try to figure out my range. What I want to do is I want to look at the graph of this function to try to decide whether that thing is increasing or decreasing, or, does it do both kind of thing. So I'm just going to look at the graph of this. So I'm going to just type into my calculator. So I'll do the square root of x minus 3, and then I have to move my cursor out from underneath the radical to do the plus 2. And to graph this, I'm just going to do zoom standard for my window. I don't know what the last thing I graphed was, so my window could be something pretty goofy. So there's my graph. It just kind of looks like this curve, right? So if I move from left to right, that curve is going up. And it sure seems like it's going to do that forever, which would make sense if we're talking about a square root, because if I take the square root of 7, that's bigger than the square root of 6 was, right? So the bigger the square root, or the number you're square rooting, the bigger the decimal is. So this is increasing. Okay with that? Because this is increasing, I know that the lower bound for the range is going to be, I get by just taking h of the lower bound for the domain. And the upper bound for the range is just going to be h of the upper bound for the domain. If it was decreasing, they switch. Right, that the lower bound for the range is h of the upper bound for the domain, and the upper bound for the range is h of the lower bound for the domain, if the function were decreasing. Right, that's why we need that, whether it's increasing or decreasing, so we make sure we get the bounds right. Okay, so I'm just going to do h of 3 then, because that was the lower bound for my domain. So 3 minus 3 square rooted plus 2. That just turns out to be 2, right? 3 minus 3 is 0. The square root of 0 is 0, and then plus 2.
So you basically plugged in the 3 for x?
Yep.
Okay.
Yep, because that's what h of 3 means, right?
Yeah.
Because you're just plugging 3 in. Everybody's good with that? So my range already, I can say my h of x, the lower bound is 2 with a bracket, and I use that bracket here because we used a 3, and with the domain, the 3 had the bracket. So the brackets and the parentheses come from whatever piece of the domain you used to find that range value. So they just follow through. This one, we'll do h of positive infinity. So that's like infinity minus square root of infinity minus 3 plus 2. Well, if I take infinity and I subtract 3 from it, it's still infinite, right? You take a finite thing and you add or subtract it from an infinite thing, it's still infinite. Is everybody okay with that? I square root infinity, still infinite, right? If I add 2 to it again, still infinite, right? So this is going to be infinity here. My question becomes, should it be plus or minus? Is it positive infinity or negative infinity? because what I'm looking for is an upper bound, I know that it's positive infinity. If what I was looking for was a lower bound, it would have to be negative infinity. Joe?
So when you're looking for the upper and lower bounds, does what you're looking for depend on if the graph is increasing or decreasing?
So the way you find the upper or lower bound changes depending on whether it's increasing or decreasing.
So like in this case, if it was decreasing, would that positive infinity be a negative infinity?
So if it was decreasing, instead of doing h of the lower bound,
Okay.
I would do h of the upper bound,
Okay.
and then I would get infinity for my lower bound,
Oh,
right?
yeah.
And since it's a lower bound, I know it would have to be a negative infinity. So it switches, but not because the increasing and decreasing, but because
You're finding different
the
bounds.
infinity that I found came from a lower bound instead of an upper bound.
Okay, that makes sense.
Okay, so then I'll just finish that up, and we're done. Everybody's okay there? Now, again, we mentioned that at the start that this was something that you could have graphed this, looked at the picture, and figured out the range without having to do that algebraically, because the directions did not ask for you to do it algebraically. You could have done it kind of any way you wanted. So the easiest way to do this would be to just isolate the lowest point on your graph, which would be this one, right? That is the point 3, 2. It looks like. I'm just looking at the tick marks. Let me just adjust the window a little bit so it's a little bit easier to see. So that's 3 over and 2 up. Everybody agree with that? So the minimum y value is 2, as we see here, right? There's actually a point at 3, 2, right? If I plug 3 into my function, I get 2 back out. Everybody agree with that? So I know it's a bracket. Because if I try to plug 3, 2 into h of x, or if I try to plug 3 into h of x, I do indeed get 2, just like we got here. So I know that that's a bracket as opposed to a parenthesis. And then this is going to continue going to the right. You guys agree? As it continues going to the right, it's going to be going up the whole time, right? Each point is going to be higher than the one to its left. Everybody agree with that? So the y-coordinate is growing without bound, increasing without bound. So it's a positive infinity. And I got that just from kind of looking at the picture. Again, the directions in this problem did not ask you to do this algebraically, so you could have graphed this, looked at the picture, and done it just from what you saw. That would be fine. Jack?
Come like test time, would you want us to do it algebraically, or would you be okay if we use calculator?
I'm gonna in this class, I'd be fine with you using the calculator. I wouldn't require you to do it algebraically. But I want to, I think it's important that you're able to see it both ways, because some people reading the graph is hard, but like grinding through numbers, I'm good with. Some people grinding through the numbers is hard, and looking at the graph, they're fine with. So this is what we did last year in Algebra 2 when we talked about domains and ranges. We just looked at the picture and found the lowest point and the highest point. Do you guys kind of remember that? I think you and Joe were both in first semester for me, right? Yeah. So that's the way I described doing it last year in Algebra 2, which is fine. This problem, the directions were such that it didn't matter how you did it. We just wanted you to do it. Okay. We feel a bit better about the homeworks here. We've seen some more examples, got a little bit of feedback on what's going on. Hopefully you've tried a couple of them and were able to go, okay, yeah, I was close on that, or like, oh, okay, I wasn't doing it right, but now I have a much better idea of what to do. I think I'm all set. Again, doesn't mean you can't ever ask about this again, but we won't see you again before the homework check. So, still though, if you're not sure on stuff, we can certainly follow up again next week. Okay. Today we're going to do 2 sections. The first section is about continuity. I'm not going to give a super technical definition of continuity because it's kind of beyond the scope of this class and requires techniques that really don't come into play until a calculus course. Instead, what I'm going to do is I'm just going to describe it kind of informally enough to where it's useful to us. So we say a function is continuous if you can draw the function without having to pick up your pencil. Okay, that there's no breaks in our graph. There are 3 types of discontinuity. So those would be the breaks in the graph. Some of which we've seen last year in our Algebra 2 class. The first type is the removable discontinuity. So let's say we have a parabola that looks like this. But I've got this open circle here, right? What does that open circle on the graph represent? Yeah, like a missing point, right? This is a parabola, but where this open circle is, there's no point there. It's missing. It's in a sense been removed. There's just like a little gap in our graph. Everybody's okay with that? Now, it still counts as a removable discontinuity if we've taken that missing point and put it somewhere else. So like instead of being where it should be, it's like, I moved it down there or something. That still counts as a removable discontinuity because I still have a gap in my graph. I still can't draw that without picking up my pencil. Right? I can draw it to here, and then I have to pick up my pencil to draw the other part of it because there's a little gap. Does that make sense? So it's just a name. The content in this section would be good enough to, if you looked at it, you could tell which one was which, and like give the x value of where that occurred. Right? So just be able to read the graph and know, visually be able to identify which one is which. So not asking a lot from this section. The second type is a jump discontinuity. This is one where you would not have seen this last year. The removable discontinuities, depending on what your teacher did, you might have seen when you talked about rational functions. But like a jump discontinuity, we would not have talked about last year. So that's like a jump discontinuity. Instead of just missing one point, you have like a whole section of the graph that's missing. And the jump discontinuity, they can line up vertically like this. Or you could have like some horizontal distance also missing. Right? Everybody's okay with that? The one thing you'd want to make sure of is that everything still passes a vertical line test. In particular, on something like this, you'd have to just make sure that both endpoints aren't closed. One open and one closed is fine. Both open is fine, but both closed would be a problem because it would fail a vertical line test at that point. Jack, you had a question?
I was just about to ask about that.
Oh, it's like I read your mind or something. Good, though. You're on thinking the same track that I was on, so that's good, right? Everybody's okay here? Again, we won't talk about like how you would have to write a function that would have a jump discontinuity in it. That's beyond the scope of what we need to do in this class. I just like you to be able to look at the graph and be able to identify, what kind of discontinuity is there. The third kind is an infinite discontinuity. And this is one that we've seen last year in your algebra class. I would think everybody would have. So let's say we have a function where we have a vertical asymptote and a horizontal asymptote, like our simple rational functions that we graphed last year. So the graph of a simple rational function kind of looked like this. Again, I'm saying that, and if you don't remember what the graph of those things looked like, that's okay. It's not a big deal. Not my expectation. I'm just making comment that this is something that we did see in class, right? This is our infinite discontinuity. Now, last year we had a different name for this thing. What did we call this? Okay, what kind? Vertical asymptote, right? Good. So here's the question. Is there a difference between vertical asymptotes and infinite discontinuity? Yes, there is. So here's the deal. All infinite discontinuities are vertical asymptotes. Not all vertical asymptotes are infinite discontinuities. So my example of a vertical asymptote that's not an infinite discontinuity, again, last year we graphed logarithmic functions. The graph of a logarithmic function had a vertical asymptote, but the whole graph was on just one side of it. I can draw that without picking up my pencil because I'm not drawing on both sides of the asymptote. So there are more vertical asymptotes than there are infinite discontinuities, right? The infinite discontinuities are like a subset of the vertical asymptotes. So they're like included inside of that definition. Just like every square is also a rectangle, but not all rectangles are squares. Or more concretely, maybe even than that, every dog is a mammal, but not all mammals are dogs. Right? That's the kind of relationship that's going on here. Does that feel okay with everybody? Okay. That's as much as I want to do with this. If you can identify the type of discontinuity just by looking at the picture, that's all I'm looking for from this section. Happy with that? So just 3 pictures to remember the names of. Oops. Yeah, okay. Never mind. There's no oops. So the next section we're going to talk about is about increasing and decreasing functions. So remember from last year, again, increasing and decreasing was like an adjective I used to describe parts of a function. So we'd say like, oh, this function is increasing on this part and it's decreasing on that part. And the way I like to think about increasing and decreasing, I'm going to just define these with a picture. I'm not going to give like a written definition of it because with what I'm going to ask you to do, I'm not going to ask you to prove anything, so we don't need a really formal definition. I'm just going to ask you to like look at a graph and tell me when it's increasing and decreasing a constant and stuff. So, okay, so I have some graph. What I'd like to do to talk about or to figure out what parts of it are increasing, decreasing, and constant, I imagine I have a little person that walks along my graph from the left to the right. This first section, the person is walking uphill. Uphill is increasing. The middle section, the little person is walking on, that middle section is flat. That section is constant. And the last section, our little person is walking downhill. that section is decreasing. Everybody okay with that definition? I'm not going to define it in words because, well, it gets kind of wordy. But talking about like your little person that walks along the graph, I mean, it's pretty simple, right? It's a simple idea. Again, the key here, the little person always walks from the left to the right, just like you're reading a book in English. I think there's languages that read the opposite direction. But in math class, we always read a graph from the left to the right. Everybody feels okay with that? Let's add in some points here and kind of describe these intervals then using our interval notation. So let's call this first point -3, 2, and I'll call this one like 5, 2. So when we describe an interval that's increasing or decreasing or constant, we're always talking about the x-coordinates. So they're always going to start like x is a member of and when we write our intervals, we're only going to be concerned with the x-coordinates. The only time where we concern ourselves with the y-coordinate is with the range, right? That's the only interval that's made up with y-coordinates. Domains, increasing, decreasing, constant, are always talking about x-coordinates. Okay, so let's start. Our interval that's increasing begins here with the left arrow. Everybody agree with that? The left arrow represents negative infinity because it's pointing to the left. And as we go left on the x-axis, the numbers get smaller. Everybody agree? And the infinities always get a parenthesis, so I'm just going to write that in right now. We stop being increasing at this point. The x-coordinate at this point is -3. And with these intervals of increasing and decreasing, all the bounds are always going to get parentheses, not just the infinities, but everything gets in a parenthesis for increasing, decreasing, and constant. So has to do with the technical definition of increasing, decreasing, constant, why none of them can be brackets. But basically it's because to show that something is increasing, you have to pick a point to the right and show that it's still uphill. If I look at that point -3, 2, if I pick a point to the right of it, it's not uphill anymore. That's why it gets a parenthesis. It can't be, the endpoints can't be included. Okay, constant. My flat section begins here. The x-coordinate there is -3. And it ends over here. The x-coordinate there is 5. Everything gets a parenthesis as we just went over. That's all there is to that. My last section is all downhill. It starts at 5. And continues to the right-hand arrow. The right-hand arrow represents positive infinity because as we move right along the x-axis, the numbers get bigger and bigger and bigger. You guys, what do you guys think? Not too bad, right? It's mostly just reading a graph and using a definition and making sure we write our answer with the proper notation. So there's no computation that we're doing here. It's just kind of just kind of reading and, looking at what we have and writing down what we see. You know what I mean? Which is nice, right? Like, let's do one more example. I'm going to just, because this example is a little bit more complicated, I'm not going to draw this one by hand. I'm going to draw it, use the computer to draw it. So first things first, anywhere where you see the graph like leaving the viewing window, you can assume there's an arrow there. So like, I have an arrow at this end, an arrow here, an arrow here, an arrow here, an arrow here, and an arrow there. Just for, just to make sure that we're all clear on that. I'm sure most of us would have assumed that's what was going on. But it's like you would read your calculator window, right? You assume that it keeps going, you just can't see it anymore. Same idea here. So far, so good? Okay. Now my question becomes, let's look for our intervals of increasing, decreasing, and constant. How many intervals do you see that are increasing? Or how many parts of the graph do you see it increasing? Joe, you say 2? That's correct.
2. Is that right?
That is correct.
Oh, awesome.
So this section here is all uphill as we start from left to right. And then this section down here, we're going uphill until we get to there. Everybody agree with that? How many decreasing or downhill sections do we have? 2. So starting at 0, we go downhill. And then starting at the other side of my asymptote, I go downhill. So do I have anything that's constant? No. There's no flat section here. So far, so good? Okay. Let's write our intervals then. So we'll do the increasing ones first. So our first interval as we work from left to right starts with the left arrow. So the lower bound is? Good. And we end at this arrow, which when I look at the x-axis looks to be at the asymptote, which is -3. Right? Again, x-coordinates, not y-coordinates, even though that arrow's pointing up. I don't care. It stops at the x value of -3. Jack?
There's an arrow. How do we know it stops at 3?
So this dashed line, that's how we drew our asymptotes, right? So you can assume that's an asymptote there, that the line just continues going up and never crosses it. Does that feel okay?
Yeah.
Okay. So now we had a gap from the asymptote, right? There's a break in my graph. Everybody agree? So now we start down here, again at -3, right? Because that's the x-coordinate where it's starting at, because it starts right up next to the asymptote. And it ends here at the x-coordinate 0. Now our decreasing starts here at 0 and goes here, which looks, again, like 3. Okay, and the next decreasing part starts here, 3, and ends with the right arrow, positive infinity. Okay, so that's a slightly more complicated example than the previous one, but again, and not really too bad. You're just kind of writing down what you see. The trickiest part is to just keep in mind that it's, regardless of what the arrows are doing, You're only looking at the x coordinate, the left and rightness of them. So it's like, where on the x-axis does this start and end? So if it's pointing up with as well as to the left, that doesn't matter. I just care about it going left or right or whatever. Or if it's at an asymptote, it's like, okay, we went up to the asymptote. I don't care that it's pointing up or down at the asymptote. I just care that it's at the asymptote. Is that okay? Right. One last topic in this section, and we'll be done for today. That last topic is called extrema. An extrema is a type of point. There are two types of extrema. There are maxima. That's just the plural for maximum. And there are minima. That's just the plural for minimum. So a maximum is a relative high point in a graph. It's basically, so it's a relative high point in the graph. There's two types of maximum. There are global or absolute. That would be the highest point or points, could be tied for first, in the entire graph. And then you can have local maximum. And a local maximum is just like the top of any hill.
It's like the highest point between two x values?
No, just like the highest point on a graph. We'll draw some examples here in a second to really clarify. The pictures is going to be easier to deal with than again, the definition here, because it's largely a visual exercise. And once we show you some pictures and talk about what these look like, it should be really clear. Minima, again, two types, the same two type. There's global and or absolute. You can use those two terms interchangeably. And then locals. I'll call it a ditch. And then there's locals minimum, which is like the bottom of any ditch. So let me do this. So let's say we have something that looks like this. This point here is the highest point on the graph, right? That's our global maximum. This point here is also the top of a hill. So that's a local maximum. This point right here is the bottom of a valley, but it's not the lowest point on the graph because the arrows are still pointing down, right? So there's lots of points below this. So this is just a local minimum. There is no global minimum on this graph because the arrows are pointing down. Any point you pick, there's always a point lower than that one. So we just say there isn't a global minimum. Joe?
Can a global maximum and a local maxima, can that be the same thing or no? Do you like?
So no,
Okay.
you'd really say one or the other. Technically speaking, every global is also local because it's also the top of a hill.
Okay.
But every local is not necessarily a global,
Okay.
right?
Sounds good.
Jack?
Say there's
So you're asking about a specific example. So let me draw what it is you're trying to say here, okay?
okay, so say there's like two hills
Okay?
that go up, kind of like the one before, but the arrows end up finishing up with their global maximum.
So you're talking about something like this.
Yeah.
So this is a local max, and this is a local max because we have arrows pointing up. This looks like the lowest one, so that would be the global min. That looks a little bit higher to me. That would be a local min, and that one would be a local min. If those were all the same, they were all the same hill, like they're kind of close, you could say that if they were all the same, had the same y coordinate there at the bottom, all three of them would be global mins. You can have more than one global min if you have a tie for the lowest.
But not max.
You can do the same thing for maxes. You could have more than one global max if you have a tie for the top. That's why when I wrote the definition, I have 4 points, right? So if you have a tie for first, that's fine. They can all be globals, regardless if you're talking about a max or a min. Is that okay with everybody? We kind of get the idea of looking at the picture and identifying these things. Okay. One thing we'll ask you to be able to do is to use your graphing calculator to actually find the coordinates of these. So actually finding the coordinates by hand algebraically turns out to be quite a difficult question. It's really a calculus question. But our calculator can do this for us, and that's a reasonable expectation for us in this class to use the calculator to do this. To do it by hand is a calculus question, and we're not in calculus. So if you'd like to follow along with me, you can take out your own graphing calculator while we run through this process of how to find the coordinates for these maxes and mins. If you'd prefer to sit and watch, that's fine too. Jack? Of course. Or if you don't have your calculator with me, it looks like we're going to be at about the 48-minute mark of the lecture if you want to go back and rewatch the lecture at home to run through the calculator part, because you're like, yo, if I don't do it by myself, there's no way I'm going to remember how to do this. So there's that too. Okay. So the first thing you'll do is you'll turn your calculator on. The on button is located in the lower left-hand corner. To be able to find the maxes and mins on your calculator, you're going to need to graph the function in question. To graph anything on your calculator, you go to the y equals button. It's in the upper left-hand corner. First things first is I'm going to clear out anything that I might have typed in there, especially for you guys where your calculator's probably not been open for 2 or 3 months. I'm going to scroll all the way down to the bottom and make sure that all of my spots are cleared out. Occasionally, if you have your calculator with the case off of it, rattling around in your backpack, buttons get pushed, and you end up with gobbledygook down at the bottom somehow. I've seen it happen lots of times, and it causes problems, so get all that stuff out of there. The next thing I'm going to check is up at the top where it says plot 1, 2, and 3. I want to make sure that none of them are highlighted. So if you see something like I have here with one of the plots highlighted, use your arrows to move your cursor up there, and then just press enter to unhighlight it. Nothing at the top should be highlighted, not plot 1, not plot 2, not plot 3. If they are, just move your cursor up there and press enter to unhighlight them. Also causes big problems when you're trying to graph. Now I'm just going to type in my function as I see it. So the X button is located next to the green alpha button. The exponent button is located above the division symbol. And then everything else is just kind of like on the home screen, obviously. So just take a minute, type that in. keep in mind with the newer calculator operating system, you have to press the right button every time to get out of the exponent. But once it's on your screen, it should look just like it looks on your sheet of paper. That always gets me on the old calculator operating system. You didn't have to press the right button to get out of the exponent. It always assumed that like you only can put one thing in the exponent if you're not using a parenthesis, which I kind of preferred. But that's what we're doing now. So, okay. Once I have this entered, what I want to do is have the calculator generate the graph of this, which means I need an appropriate viewing window. I don't know the last time I used my calculator, so I have no idea what the window is, but what I can do that's easy is if I press the zoom button, one of the options there is Z standard. That's going to give me a window going from -10 to +10 on the X and -10 to +10 on the Y. More often than not, that'll probably be a pretty appropriate window unless you're doing like the graph for a crazy story problem where like you're talking about like millions of people or something. But in this case, it gives us a pretty nice looking picture right there without having to adjust the window manually. You could do it manually, but like looking at this, I have no idea what's going to be appropriate or not. So just starting at the normal standard window and then changing from there. If it's like, oh, that's not wide enough, or oh, that's not tall enough, I can always change from there. But this did it. Everybody okay so far here? Looking at the picture, I see a global minimum right where my mouse pointer is. I see a local maximum where my mouse pointer is. And I see a local minimum where my mouse pointer is. There's no global maximum because the ends of the graph keep on going up forever. So I'm just going to record that information, and I'm going to make sure that I write my information as I see it from left to right. It just makes my life a little bit easier if I write these in order from left to right. So I have a global min, a local max, a local min, and then I'll make a note that I have no global max. Everybody okay there? Just recording what I saw when I looked at the screen so I know where to put the points that I find. So I'm not sitting there going, oh, was that a max or a min or what was that? I'm going to just find them in order. Okay. The menu that I'm going to need to use to find these maxes and mins is on my calculator. To get to that menu, I'm going to press the second button, that's the blue one, and then the trace button, which is in the top row of the calculator. The first maximum or minimum I see going from left to right was that global min. Which of these operations sounds like the one that I need? 3, the minimum operation. So I'm going to go ahead and press enter. At the bottom of my calculator, it says left bound. What the calculator is going to ask me is 3 questions. It needs to know between what 2 points should I look for this minimum, and then where should I start looking. So the left bound, it wants us to pick a point on the left side of the minimum that we're looking for. So here's my minimum. So anywhere over here would be a good point to pick. So I'm just going to use the arrows on my calculator to move my cursors. You see the cursor. Just move it till it's somewhere over there. That looks good to me. It doesn't really matter as long as it's on the left side of that minimum. And then press enter. Now it's asking for a right bound. So I'm going to move my cursor somewhere over here. And then press enter. So just use my arrows to go to the right a little bit. That looks good there. I'll press enter. And as long as I have only one extrema in between my left bound and right bound, the guess doesn't matter. So I'm just going to press enter right where it is. And there's the point or the coordinates for my global minimum. So I'm just going to copy that down onto my paper. I'm just going to round this to say 2 decimal places seems appropriate. The directions in the homework probably would ask the same thing, to round to 3 decimal places. Everybody okay with that? Let's do the same thing to find the global maximum, or I'm sorry, the local maximum. So to do that, I'll press second and that trace button once again. But this time, since I'm looking for a local maximum, I'm going to choose the maximum command. It's going to ask me for a left bound, so somewhere over here is where I want it. So I'm going to move my cursor over there. That looks good. Press enter. And then a right bound, so I want somewhere over here. That looks good. I'll press enter. And I guess just right where I'm at is fine. And there's my next point. So I'll copy that one down. Again, rounding to 3 decimal places, just because. You have to, I don't want to write all the decimal places down. 3 seems enough that I know that you use the process to get the answer and without having to write down a million numbers. You know what I mean? And the last one, the local minimum, right here. Why don't you guys try doing that on your own if you're following along? Make sure you can get it. I'm going to do it at the same time so you can check yours against mine, but I'm not going to say what I'm doing. It'll just show up on the screen.
They're all by like 0.0 something, that's fine, right?
The calculator should have given you the exact same number as me.
Oh, okay.
I don't know why it wouldn't have unless you typed something into your function wrong. But your number on the calculator should match my numbers. Maybe the very last digit might be different because of the programming might have like a round point different than the program on mine because we have different versions of the same calculator, but
Okay.
I would even find that maybe a little surprising. But the calculator is using like an approximation. It's not actually doing the calculus to get this point exactly. It has like an approximation algorithm that gets the same answer within some number of decimal points of accuracy. So it's possible that depending on the operating system, that number of points of accuracy might be different. So if you have a more recent calculator, it might be a different level of accuracy than an older calculator. But I don't know enough about the specific ins and outs of the programming to say any more than that. Okay, one other thing we can get from just this information. Assume that I never saw the graph and I was just given the function. Actually, I was just given a list of the extrema, like we have as our answer. And all I'm told about my function is that it's continuous. I can actually determine the intervals of increasing and decreasing just from looking at my list of extrema with the knowledge that the function is continuous. If it's not continuous, there could be other breaks in my intervals that I wouldn't know about. But the way this works is I'm going to look at my list of extrema here and identify the one that's the furthest to the left. It's easy to do that because all I have to do is look at the x-coordinates and find the smallest one. So we start at a minimum. So my graph must start looking like this, right? Okay, so that start is decreasing because we're going downhill. We're starting from negative infinity, and we're ending at the x-coordinate for that minimum. Oops. Then from that minimum, I'm going to a maximum. That section is increasing. So I started at the global minimum. So I write that x-coordinate. And I end at the local maximum, so I write that x-coordinate. Everybody still so far so good? From the local maximum, I go down to a local minimum. That's decreasing. So that section started at the local max. So I write that x-coordinate. And it ends at that local min. So I'll write that x-coordinate. And then after that local min, nothing else occurs, so it just must be the other side of the valley. That's increasing. So I start at the local min and continue to the right forever. And I have written my intervals of increasing and decreasing and sketched a reasonable facsimile of my graph without actually having to do anything with my calculator, right? I just kind of reason things through. The big takeaway here is that these endpoints, or these x-coordinates, I should say, for my extrema are the lower and upper bounds for my intervals of increasing and decreasing. Everybody's okay with that? And that's where we're going to end today. So for your guys' homework set, we're going to add numbers 13 to, 18, sorry. We don't meet again this week before the homework check. So I'm going to make this assignment part of the homework check for next Sunday, not this Sunday. So I'll have a separate assignment you'll see pop up in My Notre Dame for next week, Sunday, where this assignment will be part of it. Is everybody okay with that? And I'm going to try to make sure that the homework check, there's always at least one class before I expect you to have it turned in. So if you run into questions, you have an opportunity to ask about it before it's expected to be done. If it looks like I've forgotten to do that at some point, please let me know, as it's a promise I'm going to make to you guys. Sound fair? Thumbs high. All right. We'll call it quits for today.